Okay, so I'll continue today and actually finish up the discussion about computer design basics. So, because now it's been 3 classes since we started talking about this, this architecture, so I'm going to jump directly to the instruction formats. I'm just going to review our last discussion with you. These are the instruction formats that we talked about, like register type, immediate type, and jump and branch type. As you all know, you don't want your hardware to do a specific job. You want a set of functions to be implemented with the hardware. The way that we classify those sets of instructions is this. This is called instruction format. When I say register type, it's not a specific instruction like add or subtract. I'm talking about a class of those instructions. So including add, subtraction, addition, XOR operation, these are all the same type, register type. The second one, immediate type, we use it, for example, to add a constant to a specific register content, okay? And there are also other use cases of immediate type. This is a class of instructions, not a specific instruction. That's why we call them instruction formats. The reason that we call format, because the way we interpret bits, because these are 16 bits, by the way, okay? The hardware, whatever the physically, what hardware observes is just a set of bits, ones and zeros. That's all. So therefore, we have to introduce format to be able to understand those ones and zeros. And here we talked about 3 different formats. First format assumes this first 7-bit to be the opcode that tells you what to do. That's the function's name, actually. What kind of function you would like to execute. Okay, that's the opcode. The rest of the 9 bits are divided into equal compartments. You can see this 3 bits is for destination register address. This is the first register that we call a source register A and source register B. 3 bits for SA, 3 bits for the other source. Okay? Immediate is very similar. You can see the format is actually the same, but we interpret the last 3 bits to be the operand because we took, for example, we would like to add a constant, like a 3, for example, to a register content. Therefore, you have to give that constant number to the computer. And in this case, if you would like to add, you know, a specific number, like 3, for example, then R1 plus 3 goes to R1. This 3 is 1, 1, right? That 1, 1, because I use 3 bits, right, in this format, specific format, then I put a 0 here. So this is my op, okay? So you read off the constant value from the instruction itself, okay? And finally, we got jump and branch. The opcode is the same, okay? Maybe you're curious. You may be asking right now in your mind, why the hell am I having these opcodes in the beginning, to begin with, right? Why aren't they different places? Because these are different formats. Yes, that could be a possibility, but in this format, we assume opcodes to be in the beginning because that would lead to simplifications in the hardware design. The control unit more specifically. Control unit design of this format is easier because you know where to look in the format. Okay? And you will learn more about this in the computer architecture. You will actually realize that this format belongs to RISC architecture. Okay? Reduced instruction set computer. That is the RISC. And if the opcode is, you know, wandering around somewhere in the format and you see the format size is also the same, it will be different in the complex instruction set computer. That's called CISC architecture, okay? So you'll learn more about the architecture in the next class, okay? However, here, I just wanted to mention that there are different formats and different sizes of these instructions might be different, which will make it more complex. However, bear with me that we concentrate on the specific, simple specific format which belongs to RISC architecture, okay? And it's easy to interpret because the opcode is always in the same place, instruction set sizes are the same, You see, there are only minor differences. In fact, here, 3 bits actually, the format of the 3 bits is the same, but the way we interpret these 3 bits are different. Okay? But that's the only difference between the formats in the middle. For example, let's just look at the jump and branch. Okay? The rest of them are kind of easier, that's why. I just wanted to jump to jump and branch. Because in jump and branch, there are multiple options here. For example, if you select, if you would like to do branch on 0, how would you know branch on 0? Well, you look at the opcode. Opcode would tell you that it's a branch on 0. And as the name implies, you go and check it, register content. If it is 0, it's given in the instruction, by the way, you see SA. That's the address of the register that you need to check. Okay? You see, we toss some rules here. Those rules that I'm teaching, of course, is not a de facto standard in everywhere. You can select your own rules, and then go ahead and define your format, and then you go ahead and implement your hardware according to the format. Okay? So what I'm trying to describe here is that this is an example. As a computer architect yourselves, or digital system designers yourselves, can have your own format. You can just, toss some format onto the table. Nobody can object to that. Of course, your, architecture or your design has to satisfy certain constraints, like a complexity constraints, like a cost constraint, or you don't want to do something stupid in the hardware. For example, calculating the same thing twice. Okay? You have to take care of all these stuff when you come up with the new format. Okay? But this is a good format. I mean, like a toy format that I extracted from your book, and it's reasonably enough, a good design. So that's why I wanted to present it to you. Okay? Don't take me wrong. There are different designs. There are a lot of variations between the designs, and one specific design addresses one particular application. Okay? So therefore, there are many variety of these designs. Okay? This is just one of them. So in this branch is 0, you see we check the contents of a register. If it is 0, then we go ahead and update the value of the program counter, which is the pointer, okay, to the instruction memory, where you are in the instruction memory. This is sign extension, as you may remember from our past lecture. The AD value comes from these 3 bits and this 3 bits. We concatenate them to get a 6-bit long bit stream, and then we treat that as a 2's complement number. And we then sign extend that, okay, to get 16 bits, because our ALU only accepts 2 16-bit long numbers, right? Remember the ALU? ALU is something like this. It accepts 2 n-bit numbers, and then it generates another n-bit number. It's an n-bit adder, for example. But of course, we want more functionality in the ALU. We add extra stuff here, like just with a simple XOR, a set of XORs, we make it subtraction, right? And then we can also add extra logic operations. Then ALU can do bitwise XOR logic, or bitwise AND logic, or bitwise NOT logic, right? The inversion. So we added all this stuff, and you actually done that in the lab, okay? To add extra capabilities to this ALU block. Okay, but this accepts n-bit and n-bit as inputs, and then n-bit outputs, right? However, this, for example, is not n-bits. So therefore, you have to extend it, okay? Since it's a 2's complement number, 2's complement form of the decimal number, similarly here, we add a sign extension to get a 16-bit number, and then we add the program counter and this, okay? You see, there's a constraint that we all implicitly impose on our system. That program counter is 16-bit long. So what that means, that implies something, right? That implies if program counter is 16 bits long, okay, that actually puts the constraint on your memory size. Why? Because you got 16 bits, that actually means there are 2 to the 16 memory locations that can be addressed, right? That's the maximum number of memory locations you can address. If you got more than that, you cannot address it because there are only 16 bits in the program counter. I'm talking about, of course, instruction memory, right? Not the data memory. I'm not talking about the RAM, random access memory. This is instruction memory, which is typically implemented in the modern architectures in caches, right? You remember L1 cache, L2 cache, L3 cache? Maybe you have seen it. You know, when you're crunching in the computer, something related to computers, you got L1 cache, L2 cache, and L3 cache. And those L1 cache, the reason that I'm mentioning them is that L1 cache is actually not a single hardware. There are two L1 caches, one for instruction and one for data. So they separated these two memories, okay? So therefore, this what I'm talking about here is an instruction memory. So that memory only stores instructions, not data, only instructions, okay? You can go ahead and ask me, can I store data and instruction in the same physical memory? Yes, you can. Yes, of course. As long as you know where they are staring in the memory, where they are located in memory, and you don't confuse them, well, that's okay then. I mean, physical memory or an abstracted memory from a computer's design perspective, it doesn't matter. Except that, of course, access latency, access times, I/O, these are different discussions that we should make. However, even before coming to that point, from a functionality point of view, abstract memory or a specific single physical memory wouldn't make difference from a computer design perspective. Because all you want is get my data from that address, right? And that's how cloud storage works, so cloud computing works. You send something to the cloud, you've got no idea where data is stored. You just extract, because when you open your browser, you see your data is there, right? But do you know where that data is located? Is it in Holland, or is it in Portugal, or is it somewhere in India? You got no idea, right? But do you care about it? No, you don't care about it. This is called abstraction. And that abstraction is not only in the cloud, it is also in our physical computers. There are a lot of virtual stuff going on, okay? To make the design easier, okay? All right, so coming back here, 2 to the 16 memory locations. This is not a big number, you know. This is 2 to the 6 multiplied with 2 to the 10. Do you remember 2 to the 10? It's 124. So it's 1K, let's say. So it's 2 to the 6 is 64. So it's like 64K, right? Something 64K. So 64,000. So it's not a big memory, actually, right? So this is the problem of the design. The program counter should be selected to contain more bits, not just 16 bits. Okay? So you see, we actually caught a problem in the design. But that's okay, because this is a toy example. You would never use it in a practical circumstances. Okay? This format or this ISA, instruction set architecture, is not something real. It's just toy example for you guys, students, right? To learn. Anyway, I'm just pointing out these details because I want you to follow what is reality and why are we learning this and what's the next step, right? Those type of questions should appear in your mind while we're discussing this stuff. Okay, so we talked about this. If you'd like to go ahead and execute branch on negative, then you should check the same. I mean, it's exactly the same, but you should check the register content. If it is negative, then you go ahead and do the same thing. If these two conditions are not satisfied, then you increment the program counter. Because remember, program counter is at the end of the day is a pointer, right? It's a pointer to the memory, right? And you got these instructions located in your memory. So basically go to the next and next and next and next and until something weird happens. What does that mean? Branch and jump. These are weird things, right? Because these are control mechanisms that change the contents of program counter. What it means is that you start, pointing to somewhere else in the memory, somewhere maybe very, very far away where you are. Okay? That's the control instructions. Okay? That's sometimes people call it control. The control class, okay? Anyway, here, jump is a direct change on the program counter. So you basically store something to the register A because that's a specific address you would like to jump to. Then that address will be your new value in the program counter if it's a jump operation. Where do we know that's a jump operation? Because you go to opcode and then figure out that it's a jump, okay? Anyway, the rest of the other classes, the program counter, these register and immediate type instructions like format, they're not control instructions, so to speak. Therefore, the program counter should increment, okay? We talked about the control bits, right, that is required to select between those control instructions, such as if you have a... First question is, do we have a control instruction or not? That is determined by PL. If we have it, then PL becomes 1. Then the next question, is it a jump operation or a branch operation? That is determined by JB, jump on branch. If it is 1, then it's a jump. If it is 0, it's branch. The next question, if it's a branch, then which type of branch is that? Is it branch on negative or branch on 0? Okay? And that is the BC control bit that tells you which one it is. The rest of them are just don't cares. Okay? So we came up with this control logic because that control logic was not part of our previous control. Remember the previous control, 16-bit long? We didn't have those bits in there because we didn't have any control instructions. We only had like simple instructions, mostly register type. Add instruction, subtract operation, shift operation, logic operations. These were what we had in our world. But we are actually expanding our world right now, widening our world, right? There's been like a promotion of Turkish Airlines. But we're actually widening our world because we're introducing new instructions that will enable the software writer to use, okay? And in fact, if you would like to implement a for loop or a while loop or an if clause, you should have a control instruction. How in the world you would jump from one location to another unless you have those control instructions, right? So, branch control, we actually feed these bits and then we create the program counter cooperation. But we also need to get some feedback from the ALU. Particularly, how are we going to check these conditions? Those conditions are already checked in by the ALU. While you're doing some computations, the ALU already have those status bits. These are sometimes called condition codes, by the way, just keep in mind. And then we feed those information back to the control, branch control, okay, to learn about where we are in terms of checking these conditions, okay? Because they're already there, so why don't we just use them, okay? Of course, these are going to be meaningful only if we have a branch instruction. If it's a jump operation, these are not going to be meaningful, okay? But of course, we didn't talk about here, but this C was a carry out, which may mean an overflow, and V also a check for an overflow, okay, in general. So we're not really doing anything about these two bits because we're not talking about, because these are taken care of by the upper layer software, like operating systems. Okay, that's why we're not discussing them. But keep that in mind, in systems programming, probably in operating systems, you will talk about them. Okay? How are we going to handle an overflow problem? Okay? That is something, because the problem is, again, this is a computer architecture discussion, but anyway, since it's come to play, so I would like to mention them. So, the thing is that if you would like to implement some problem, some solution to the problem, okay, there are two ways. You may implement it in hardware, you may implement it in the software. Both are okay, from a functional point of view, okay? Well, we're doing all these ones and zeros, we're adding, for example, we have got an ALU in the first place. We are adding two n-bit numbers. Can you implement this on the software? Yes, you can. Of course you can. But would you prefer it? Probably not, because this is a very low level, computation. You would probably prefer it to be fast, and hardware is blazingly fast compared to software, okay? So that is, again, computer architecture's decision. But if you have got an overflow and you want to handle, for example, you have to erase some of the register contents because there's an overflow, so things can go wrong. So you may want to erase some of the register contents to empty them out so that you can start a brand new computation. Well, should this be handled in the hardware or should this be handled on the software? That's a design question, okay? And there are different type of services. Sometimes they're implemented in hardware. Sometimes it's implemented in the software. Okay? There's no direct answer to that question. Okay? It depends. It depends on the application. Okay. Let me continue. Okay, so this was one of the things I didn't talk about specifically, but this is just an example that I actually shown you last time. This was the thing that we discussed, and I said, oh, there's a similarity between the opcode and the function select inputs, if you remember. These are not randomly assigned to these instructions, right? And those are the description of those instructions. As you can see, we've got a bunch of instructions. Most of them are register type. Particularly, these are all register type, you can see. And there are some of them are also here, like shift right, shift left, these are also. And then we got these immediate type, like load immediate, add immediate. That's the second type, the second format. And we got these memory operations, okay, because you would like to write or read to memory. And there we also talked about address calculation, right? Because here you see load immediate, we got this, this is immediate type, by the way. I'm sorry, sorry about that. We got load instruction here. You see the content of a register becomes the memory address, right? And then we write to the register. And we got the store operation. The contents of a register is written to another content of a register becomes the address of the memory that we write this content to that memory address. Okay? So there are two registers here. You see SA and SP. One of them is the data, user data. The other is the address that we would like to write this data to. Okay? And that address is the memory address. Okay? You see the memory address is bound to be the number of bits we store. The memory size is bound to be determined by the register size. Because register size, if it is 16-bit long, then you can actually address 2 to the 16 memory locations, right? That also is an important observation here, although it's very implicit, but that actually tells us that the memory size is constrained by the register size. Okay? You can see the branch on 0, branch on negative are as defined, and jump is here. And you see the opcodes are different, right? And that's why I always keep saying that the opcode determines the functionality. Question? Yes, sorry.
Can you tell the difference between load and store?
Load and store, the difference? Okay, so load is loading something from the memory to the register. So let me go back to the data path for you. Okay, so let's just go back to the data path real quick. Okay, here is my data path. That's a high-level description of the data path. You see there is a wire coming in here. This is the connection to the memory. Okay? If you would like to write something from the memory to the registers, then you use this connection. So ND select must be 1. Okay, so that puts this here, then you have to provide the destination address, so it's going to be written to here. That is load, okay? The store on the other hand, is about writing something that because you do some calculations here, right? Like addition, subtraction, that's what the chip is built for. It does some useful calculations. And at the end of the day, you come up with some number that needs to be displayed, okay? Therefore, this needs to be displayed. Okay, let's just send it to display, okay? But what you do is you copy that, send it to display. But that register content still has that value, has that data. But the problem is, this chip wants to do something else. What are you going to do with this data? You want to erase it? No way. You store that information to memory so that you can erase information here. Okay, that is called memory access. That requires you to call some store instruction. Okay? Store instruction does the following. It takes the data, puts it here in this bus by appropriate selections of this must select, etc. Okay, or AB selects. Okay, and it puts it here, data out. Okay, so it has to be B data. That is your data, right? Because you see, it's data out. How about the other bus? That bus needs to be filled in with the memory address you would like write to. Okay, you have to provide the memory two things, data and write. Okay, data, write address, and data. And of course, maybe a control bit, whether he wants to write it or read it, right? So, that's what this is telling you. So let me go back to instruction. Okay, here we go. We have load. You see load? The register content is an address. Okay? So you go to that address, just provide that address in source B. Remember the bus B? That is bus B. That is sent to the memory. Okay? And memory read is enabled. It reads the value and puts that data on the, remember the ND select? That was a, at the bottom there was a, a wire coming from outside. That is the memory, actually. The memory puts the data on that bus, and that bus actually goes into your, through that mux at the bottom, through your, through your chip, and so you can write the data to an appropriate register, destination register. Okay? So that is this. Store, on the other hand, is about the top part of the chip, that you don't even go through the ALU, right? You don't use ALU. That's why the function select doesn't matter. You basically put don't cares for the function select because you don't care what type of operation you want with the ALU because it's not going to go anywhere. It's going to stay in the chip. So here, what this means is that the register content now in this case is the data that you put on the source B. That's why we have SP actually. And you also have an address that is written in source A. Whatever the register that has the address, for example, R2 has the address. Then you have copy that, you select that address value, put it in source B or bus A, because it's source A. Bus A. That bus A now determines your address. You push it out and push also this address is pushed out. You also push the data out by selecting appropriate register and putting it on the bus B. That is also pushed. Then you enable memory. Data is written. Okay? Okay, any more questions? Again, these opcodes determine the functionality, so you know where you are. Okay? For example, by just looking at this bit and this bits, you can know, oh, this is a load, or this is a store. You identify them through opcodes. All right. Okay, so this is an example. How about I'd like to execute this one instruction, R2 minus R3, and the result is written to R1. Perfect. I actually know by just looking at this instruction, I know the destination register R1, which is 001. Okay. First register is the source A actually is R2, 010. All the source B register is R3, 011. Right? That's why you have all these bits here. You see, you can actually, it's like a table lookup. Okay? Nothing more than that. It's just a table lookup. How about subtraction? Well, I know what subtraction is by just looking at my instruction set architecture here. Right? What is subtract? 0, 0, 0, 0, 1, 0, 1. Okay, that allows me to do the subtraction, you see? A and B. You have to use the table because somebody has already designed it. Okay? If you don't comply with these rules, then your calculation will be wrong. Okay? That's why I said instruction set architecture. This is instruction set, by the way. This is a contract between hardware engineer and software engineer. They meet at this particular point. Who determines it? It's architect. Architect does write all these sets and then defines the relationship so that the hardware and software writers will know what to do. Okay? Otherwise, they will not know what to do because language is not there. How are they going to communicate? Right? So here you see is here, subtract, and you're done. Because you have got the instruction the hardware understands. If you send this, if you store this in the memory, instruction memory, and program counter points to that, reads this, that's called fetching, by the way. It fetches this to the chip register. Okay? Most likely there is a register between the chip and the instruction memory that is called instruction register. Okay? That is called instruction fetch. So we fetch this instruction. We fetch this instruction to the instruction memory. Then we decode it. Decoding meaning that, what is this? Oh, this is subtraction. Okay, so what am I subtracting? Well, you have to go to source A and source B. Okay, when I subtract them, where am I going to write the result? Okay, it's there, destination. So it tells you everything. But the way that you understand the format is opcode. The opcode is the most important, because without that, you will never know what to do with the rest of the bits in the instruction. Okay? For instance, here, if you don't memorize it, of course, you would not know what this is, right? But I'll tell you what it is. It is a move operation. It's pretty easy operation. Maybe the simplest possible instruction ever you can find in any instruction set architecture is the move. And it is always there, right? Because you always have to copy information from one location to another. It's just part of the program store architectures. Okay? So you can see here that I take R5 and move the content of R5. Oh, this is not a move operation, guys. Sorry about that. I take it back. It's a store operation because there's a memory here. Since I didn't memorize, just like you, I couldn't, figure it out. So here, the question is about storing information. So all you have to do, R5 is what the data that you want to write to memory. That's the R5 content. Then you write to where? Address that is stored in R4. Okay? So therefore, this is memory write or store information for. This, we don't care because there is no destination. All we care is these two bits. You see, you always put some X's here just to show that there are don't cares. But in hardware, you have to select something. And most likely you will select zeros. It's just by default value. Okay? But you have to choose a bit. For example, in quizzes, I read your quizzes by the way, some people just put zeros instead of don't cares. I couldn't give points to that because I want to know whether you know that it's a don't care or not. So in the exam, if it's a don't care, put an X. But in hardware, you can't do that. Okay? Just keep that in mind. There's a difference between the exam and the implementation. Okay. This one is at immediate. You see 3 is added to R7 and then results are 2. This is the opcode for the immediate. This is your 3, by the way. You see, this is not treated as a register address. This is treated as a decimal 3. How am I going to know that? Well, opcode tells you. Opcode is an immediate, at immediate opcode. Okay? At immediate operation. So this is 3. This is your address, R7. And the result is written to R2. That is the destination. And finally, there is a branch on 0. You see, if R6 is 0, then you subtract 20 from the program counter and you update the program counter. How am I going to get this minus 20 is, again, according to the format, right? Remember branch and jump format? I took this 3 bits and then take this 3 bits, concatenate them. We got 6 bits, right? We got 6 bits, which corresponds to minus 20. You see, you can actually see that this one actually tells you that it's a negative number. You can go ahead and check it if you like, if you don't believe me. And please don't believe me. Go and check yourself. This 101 is concatenated with 100 to make up minus 20. And that minus 20 is sign extended, which is not shown in here, but it's sign extended to make it 16 bits. And then it added to the current value of the program counter, whatever that value is, okay? And the result is written to the program counter. But this, of course, happens if you check the register address 110, which corresponds to R6, and check that if it is 0. How are you going to do that? Well, you put R6 in one of the buses, okay? And then put a 0 in another register, for example, and then put that in the other bus, for example, bus A, bus B. That goes through the ALU, right? If they are equal, then there's a condition code for that, right? If it is equal, 0 means equal, actually. So if they are equal, that 0 condition code, or let's just say status bit, is 1, telling you that this is satisfied. So you also have to check this in your hardware. But checking this is pretty easy with an AND gate, right? Just put an AND gate. If that is 1, and this condition, that means its condition is satisfied, right? If it is 0, then AND gate will always push a 0, so that will disable your the rest of the hardware, right? So checking is something is pretty easy in hardware by just putting an AND gate. Okay, anyway, so this branch on 0 is determined by this opcode, and these are interpreted the way that I just described the format. That's why the format is important, because without the format, you would not be able to interpret these bits. When you look at these bits from that distance, they're just random zeros and ones, right? But they are not. They're based on a specific format. Okay? That's why it's, hacking a hardware is harder compared to hacking a software, because software is more user-friendly. Hardware is not that user-friendly, because it depends on the way that you design these formats and etc. The hacker has to know the entire format. And believe me, this is a toy example. Maybe some of you guys are still having some problems following what I'm saying. However, in reality, the formats are very complicated. Particularly just, Google it on the Intel's, recent architectures. The x86 architecture, for example. Just look at it. How many instructions they support? Thousands of them. And there's a CISC architecture, actually. The instruction format is not fixed. The size of the instruction changes, opcodes are everywhere, these register addresses are everywhere. You have to do a lot of logic. They put a lot of logic in their design. So it's pretty hard to, even understanding the entire instruction set architecture is very hard. And let alone all these ones and zeros you extract from the hardware to be able to understand what's going on. Okay? Anyway, here's the complete picture, guys. So we completed everything, right? Except the instruction decoder, which I'm going to talk about. Okay? But everything that component by component, we went through. Okay? So here's my data path, right? Here's my data path. And I actually left some of the control bits floating in our previous classes, if you remember, such as, these V, C, and Z, they're going out, but where they're connected. Now we know where they're connected. Right. They're connected to branch control. Okay? You see, we didn't really wire them up because it's gonna make it messy. You don't want, your design to look messy. In reality, of course, you have to connect them. But in illustrations, we actually refrain ourselves putting all these wires everywhere, so it's not going to look messy. Okay, so here, data memory is now here, you see? And one of the control bits that we were missing was the NW, right? That is the memory write and read control bits. If it is 0, you read. If it is 1, you write, okay? Whenever you have a sequential memory element in your design, please put a control bit to write and read, okay? Otherwise, your data may be corrupted. It's at risk, okay? So in order to leave that risk to 0, put a control bit here. Okay, now data is, you see those wires were just going out and it's not connected. Now it's connected. It's connected and part of the architecture here. You see this 0 field wasn't here, but now it is, because if you got instruction coming in, and we know that the first, the least significant 3 bits was op, right? Op. But we have to put something here to make it 16 bits, that is 0 field, okay? So it's there. Here, sign extension is also part of the thing, because program counter should accept some negative numbers in order to go back and go forward. However, here, this 3 bits here is just 0 filled. The reason being, we assumed in this architecture that 3 bit to be always positive number. Okay? We could have done it by negative, by the way, but that would constrain our problem because I've got only 3 bits, right? So that means I can only represent 8 possibilities, which actually put me a constraint on the extent of numbers, like -3 to 4, right? So instead of doing that, I actually extend my number to only make it positive, so I can extend it from 0 to 7. So 7 is a relatively large number. That's why we did that. But this is again free. Don't take it as that's the only way. That's not the only way. You can actually make it sign extension, put in a sign extension in your design, and make the negative numbers a possibility. That's a possibility. That can also be done. Okay? There's no harm in that. But I just assumed that I would like to add like 6 and 7 to my architecture. That's why we assume, like the book assumed, that to be a positive number. Okay, now everything is connected, right? Do you have any problems concerning the data path, memory, and the control logic here, program counter and instruction memory? Because next is producing the control bits. Now remember, we already had 16 bits control bits. Remember those 16 bits? They were destination, 3 bits, source register A and source register B, 3 bits for each, MB select for one of the muxes, FS, function select unit, 4 bits, right? MD, 1 bit at the bottom. Remember the data path? Here, MD. You see, the MD is right here, but it's not connected to here, right? But it should be connected, of course, in order to carry information. Okay, RW is for reads write for the register file. Sorry about this. This is just killing me. So we have RW to control writes and reads in register file. Remember, this is a good practice to put a control bit here, RW. MW is new now, right? Because up until here we have 16 bits already. Now these are new ones. MW is the memory write read, 1 bit. PL, oh, is there any jump or branch or control instruction or not? JB, or is it a jump or branch? And this is which branch? Branch on 0 or branch on negative, okay? So we got everything now set out, because you see BC, JB, PL are connected to here, MW here, and the rest of them you already know. These are 16, the other rest of the 16 bits that feed those muxes and data, oh sorry, not that, the register file, you see, and function unit, okay, the ALU, the core of the matter where the all computations take place, okay? Now, everything is connected. You see, it's a self-contained chip, okay, that does some useful information processing, simple processing, but that's still okay, okay? But you see, it's a self-contained, and it's only taking 1 clock cycle to finish everything here. It's only 1 clock cycle, because in the next clock cycle, register file contents will be different, and memory also will be different. These are sequential logic operations, right? And they are bound to change at every rising edge or falling edge. That means there's only 1 period of time to complete everything here, and you also push the control bits so that you have this particular operation implemented by the data path, and the result is either written in the register file or in data memory. Or maybe you read something from the memory, but it's going to take only 1 clock cycle, okay? This is why we call it single cycle computer, okay? Instructions need not to finish in a single cycle, and as you know from your project, add instruction takes 3 clock cycles. Right? Subtraction operation takes 3 clock cycles. So that is called multi-cycle computer, okay? Since I have got a single cycle already had time to discuss in the class, that's why I put the multi-cycle example to the project, so you learn maximum, okay? Maximum possible from this class, okay? But very similar. In multi-cycle is also very similar because now you distribute all this stuff to multi-cycle. For example, how are you going to send those control bits? It's easy. You just delay some of them, okay? You can actually put some, registers. So that means it's going, for example, if you put this DA, BA, EA to a 9-bit register, and these are all connected immediately, but that is into register, and then from register to the corresponding locations. Well, that will put a delay, right? So if you need DA, BA, AA in the next clock cycle, then put a register, okay? That's the only difference, actually. It's not the only difference between single and multi-cycle, of course, but to the extent of the project, it will be just sufficient to know that, okay? The rest of them are just the same. Okay, this is looking good, by the way. So I'd like to comment 2 things here. First one, the instruction decoder, which I'm going to show you now. What it is, well, how it's actually taking this 16-bit instruction and turning it into 20-bit long control word, right? How is this going to be implemented? The approach that we take is hardwired control, okay? That's why I call it single cycle hardwired control plus the data path. What is hardwired control? That means instruction decoder is combinational logic. It only contains memoryless elements, okay? No sequential logic, okay? Why are we calling it hard then? Because when you design this, if you have, for example, extra instruction you would like to put it in your format, then it will actually change the instruction decoder entirely. Because you have to make up for that instruction. Because that instruction will change some of the control bits. It's not easy to just do a little tweak here and then adapt the entire hardware to that specific change in your instruction set architecture. Okay? That's the reason that we call it hardwired. It is really fast because it's combinational logic, but the problem is that if you'd like to just add a simple instruction, extra instruction, for example, an instruction that does addition and subtraction at the same time, maybe. Or maybe we don't have AND. Do we have AND in our instruction set architecture? Maybe we have. But let's just put it, for example, another extra logic operation. So let me just check it first. These are our, yeah, so here, you see AND and OR already there, XOR and, you know, this.
Right.
So for example, if I'd like to add, Nand Gate, for example, right? In order to implement the Nand Gate with this instruction set architecture, you have to first put it into a NAND, and then the complement, right? So that requires 2 cycles, right? Because each one of them takes 1 clock cycle. So that means you require 2 clock cycles. Just to implement the NAND would take 2 cycles in here. You may ask yourself, oh, this is too much time for just a specific NAND, right? So you may want to introduce a NAND here that would take only single cycle, okay? You would think that, oh, that's just a simple change in the instruction set architecture, but that probably would not change the hardware too much. Yeah, the data path, the control bits may not change too much, but instruction decoder will change a lot. The reason that it's because combinational logic, you did all these kernel map stuff, right? Minimizations. You know, for example, from the kernel maps, if you take 1 bit away, you will realize that the optimization will change, right? And if you add 1 specific bit, you may actually come up with a kernel map, for example, just to give you an idea, you know, what's happening. For example, here, okay, if you've got an additional 1 here, that means, let me just put a dot, dot, dot. That means you can actually simplify it by just taking this entire set, right? It's going to just give you a single letter simplification. But if you don't have this, then you have this thing, and this thing. You see how the Boolean expression gets complicated? That's what I'm talking about. But just a single one can change the design and make it more complicated or easier, depending on the circumstances. That's why I'm saying, by just adding a NAND gate will actually change your design because your combinational logic design actually based on these optimizations. Okay? An instruction decoder is a combinational circuit design. The only problem here is that based on the previous treatments of ourselves to the combinational logic design was there's only 1 output and there are 3 to 4 inputs, so it was a pretty easy input-output combination. However, in the instruction decoder here, you see 16 bits coming in, and each one of them is an output, function output. That means 20 different functions. You should actually draw for 16-bit inputs, that means 2 to the 16. So the kernel map is 2 to the 8 by 2 to the 8. It's a huge kernel map for each one of these bits, and you've got 20 of them. Not only you have to optimize per function, but you also have to optimize cross functions. So it's going to make a lot of effort, okay? But the thing is that if you realize there are many simplifications already, you don't even have to go through kernel maps optimization. Okay, this is the general section. And here is, you see, you don't have to put them everything in here, but we actually did classification of these instructions, such as function unit without a constant. What happens to these bits, starting from 15, 14, 13, 9, and MB, MDR. Why am I starting 15? Because the rest of them, destination register, source register A, source register B, these are simple, right? You don't have to change them, just copy them. The rest of the bits are important, this one. 15 to here, BC, okay? And you see 13, and these are also probably function unit here, so it's already known. So these are the important ones. And these are the class of instructions we would like to support. If you just put ones and zeros, there's also a similar table in the project, at the end of the project description document. Okay, similar table here. This is a bit more complicated compared to the project, by the way. But all you have to do, put some zeros and ones and don't cares in different places by just looking at the data path. Which switch you should turn off, or which switch you should turn on. These are them. For example, MD, MD, RW, MW, PL, JB, BC. You see, for example, for memory read and write, are you doing any jump and branch? Of course not. That's why we have got don't cares here. Okay? For instance, branch on zero, branch on negative. Of course, these will matter. Okay? How about MD? Well, you don't even care about MD because this is about branch and on zero and negative. MD is the last mux operator that has got something to do with the memory load and store. Okay? And so that's why we got memory read and memory write for this MD to be, for example, 1 and don't care. Okay? In the write case, it's a don't care because you don't use it. But for read case, it matters. Right? It matters. You have to take that input and then put it into your bus. Otherwise, it will take the function unit outputs. Okay, so when you look at this, it turns out that so 15, 14, 13, 9, these are kind of easy. Just take them out from the instruction directly and copy to the control word. However, MD, MD, W, MW, PL, JPBC are not that easy. But it turns out that, for example, MB is just a 15 bits in the instruction set. You see, instruction set is just 16-bit long, right? Excluding this 4 bits here, because as I've shown you before, those 4 bits actually identical to function select units, function select bits. So that's why I'm just taking them out. But the rest of them is just 16 bits. And based on that, MB, for example, turns out to be the 15-bit. MD turns out to be 13 bits of the instruction. RW turns out to be 14 bits complemented. Okay, MW similarly can be found, but those are just simple Boolean expressions. Okay, you see an AND operation and negated 15 ended with 14, etc., etc. Okay, and it turns out the control circuit actually is very, very simple. You see the instruction on top at 16 bits long, and the control word here. You see that's what I was talking about. The DA, AA, and BA, they are directly coming from the opcode. You're not really doing anything here. Okay, but those MB, FS, FS is also was coming directly from. Oh, it's not coming from the instruction. Sorry, it has to be decoded from the opcode. Okay, so FS is here. MD has to be calculated. RW, MW has to be calculated. But you see the JB and BC, they are kind of, a copy operation, you see, because that we figured out that JB and BC, okay, coming from the opcode, it has to come from opcode because otherwise we cannot identify whether it's a branch operation or a jump operation, okay? This requires some thought, okay? I'm not saying that, well, I came up with this picture to you. I know it's not kind of straightforward to see, how are we coming from. You have to ponder a bit deeper about this table, okay? If you just go, row by row, and then convince yourself that this table is right, then you will realize that these are the Boolean expressions, okay? So you don't need to draw corner maps. So my suggestion, my recommendation, so this is the gist of the story today. If you got like 16-bit input, 20 bits output function design, you don't draw corner maps, particularly if you're doing it by hand. If you've got a computer, yeah, you just feed it in the computer. Computer will come up with these stuff, so you don't need to worry about the control design, okay? Because it tells you what to do. And there are softwares like that, by the way. But if you got like 100 inputs, 20 hundreds outputs, then standard approach would not work, okay? Because it's going to, the number of possibilities will be, humongous. And it goes exponentially many possibilities, and a classical computer cannot deal with that much computation loads. So therefore, you basically think about the class of instructions and then draw something like this, okay? And it turns out that the Boolean expressions are easy, and this is your final circuit. The final circuit, the instruction decoder, is basically using 3 AND gates and 3 NOT gates. The rest of them are just wires. You see? And if, as I said before, I'm coming back to my previous discussion, if you add a Nand gate or something else to your instruction set architecture, this will change. Okay? I don't know, I can't predict how many of changes you should have here, but it's going to change. And probably dramatically. Okay? This is the problem with the hardwired control. Okay? Rather than designing this circuit, oh, how am I going to come up with that? Just assume that there's a software that does that for you. You probably, please focus on the general idea. Okay? The general idea here is that this is a hardwired control, and hardwired control can be a big problem when you have extra instruction your hardware you want to support, and you want to take some instruction from the instruction set because it becomes useless in the future. That is also problematic because if you just put it out, maybe your hardware will be minimized. There will be lots of minimizations. So your cost and energy consumption from those perspectives, your hardware is not optimal anymore. Okay? Because of the backward compatibility issues, usually people leave those instructions part of the instruction set architecture in many cases. But at some point, like for example 20 years later, maybe you want to get rid of them, but that would require an entire, a ground up approach. So you start from your beginning and scratch and then design your chip, okay? From the beginning. Okay, this is a single cycle, hardwired control plus data path computer, okay? There are several limitations. First of all, as the complexity of the operations increase, you see the instructions are pretty easy. Add, XOR, shift, branch, jump, these are kind of easy instructions. But if your instructions, in other words operations, micro operations, complexity of them increase, then it becomes very hard to complete the operation in a single cycle, right? Because you have to complete your instruction operation within the same period. The next rising edge would cause changes in the register and memory contents, okay? So therefore, you have to be really careful. You have to choose your period based on the highest complexity instruction. But would that be fair to the others? No. Because the others would only take 10%, 5% of time of the entire period. Then what's going to happen the rest of the time? Well, CPU will be idle. It will wait for an instruction. But there is no instruction because that period tells you how long you should wait for the next instruction because it's a single cycle computer, remember? That is the problem with the single cycle computer. Considering the worst case delay path, okay, meaning that worst case meaning because there are gate delays, right? In addition to the register reads and writes, there are gate delays. ALUs, they're not doing everything in 0 seconds. There's a gate delay. The gate delays that you accumulate throughout the operation, okay, for any specific instruction would be different. It will vary from one instruction to another. So when I say worst case delay path, that is the delay path of the most complex instruction in your instruction set architecture. Okay? For example, add operation, maybe. Okay, that's the worst case delay path. The clock frequency as well as the rate of the operation will be limited by a single cycle because you determine your period based on the worst case delay path. Okay? There are advanced techniques to deal with these problems. Multicycle computer, okay? That means an instruction is implemented or executed in multiple cycles, as you know from your project. However, while you're doing it, in the first cycle, okay, I divide my add operation into 3 sub-adds, let's say, sub-additions. In the first cycle, I do the first sub-addition. In the second cycle, in the second sub-addition. Third cycle, third sub-addition. Okay, that's good. Probably those sub-additions using different parts of the hardware. Okay? Okay then, when I do first sub-addition in the first cycle and I move into the second cycle doing the second sub-addition using different hardware, what happens to the first hardware? Would that wait? Maybe not. Maybe it's going to accept the first sub-addition of the next addition, right? That is called pipelining. So you basically put the instructions, like interleave them, because now the instructions are multiple. There are multiple sub-computations that associated with each instruction. So why don't we just interleave them? Okay? That's also going to be a part of the discussion of computer architecture class next year. So I'm actually now developing some type of motivation for you for the next class. Okay? All right. Anyway, I stop here.